Hey class, today we are going to talk about hybrid orbitals. First, we are going to discuss what a hybrid orbital is and how it forms. Then we are going to talk about the three kinds of hybrid orbitals that you are going to need to know, and then how to determine the hybridization in a molecule. All right, so let's talk about hybrid orbitals. First, let's just remember what an orbital is. An orbital in the quantum mechanical model is a place where you are likely to find electrons. So that's an area around the nucleus where you will probably find electrons. And there are four types of atomic orbitals. There's the s, p, d, and f orbitals. And today we're going to focus only on the s and the p orbitals specifically. So to remind you what the s and p orbitals look like, this is what an s orbital looks like. It's spherical. And then p orbitals come in threes. And remember, there's 2 electrons in every orbital. And you have px, py, and pz. You can actually write the electron configuration, of course, for an element using something called an orbital diagram. So this is a simple orbital diagram, and you'll notice that there's an arrow that points up, showing how each orbital is increasing in energy. So your first energy level has a 1s orbital, and that's it. Your second energy level has a 2s and a 2p orbital. The s is, of course, lower in energy than the 3 2p orbitals. And we're going to be focusing on orbital diagrams for just a minute. So if we look at the electron configuration for carbon, its electron configuration is 1s2, 2s2, and 2b2. Has a total of 6 electrons, and we can actually draw those electrons as up-down arrows in our orbital diagram. So the orbital diagram shows us which orbitals these electrons are located in. Now, the issue that we have with carbon specifically, its atomic orbital diagram, is the following. According to carbon's orbital diagram, it really only has 2 places for electrons to be shared from another element. Remember, electrons are always shared in pairs, so it has 2 electrons, and then, another element can come in and share its 1 or 2 electrons and form 2 bonds. And we know that's not true for carbon. We know through experimentation that carbon always forms 4 bonds. And so its orbital diagram with its atomic orbitals doesn't really explain how it's possible for carbon to form 4 bonds. And even if we were to take one of these electrons, say this electron, and promote it up here and move it up to the 2p energy level, that still only gives us 3 bonds. And so it doesn't really make sense for how carbon is capable of forming 4 bonds. So how is that possible? Well, we now know it's possible because of this theory called orbital hybridization. So orbital hybridization is the combining of atomic orbitals into new hybrid orbitals that are equal in energy. So orbital hybridization is mixing of orbitals, where we take s and p orbitals and they kind of merge and mix together and form a whole new orbital that's called a hybrid orbital. So we're going to learn about 3 types of hybrid orbitals. And I'll go ahead and tell you what they're called. There's an sp3 hybrid orbital, there are sp2 hybrid orbitals, and there are sp hybrid orbitals. And we're going to go through each one and discuss how they form. All right, so sp3 hybrid orbitals. We're going to use methane, CH4, carbon tetrahydride, as our example, and we're going to be looking at the carbon and the hybridization of that central atom, carbon. So here's carbon's orbital diagram from its electron configuration. So this is its atomic orbital diagram. And so for hybridization to occur, we know that carbon is going to take one of its 2s electrons and it's going to promote it up to the 2p energy level, or 2p orbital. Next, we know, or we think, that the 2s and the 2p orbitals are going to mix. So we're going to get a mixing of these, of one s orbital and 3 p orbitals. So what it looks like after it mixes is this, right here. And so we had this mixing, and now we have 4 orbitals, and these 4 orbitals right here are a combination of, if you remember, 1s and 3p orbitals that have all kind of mixed together. And we call these orbitals sp3 hybrid orbitals. They're hybrids because they're a mixture of 2 things, just like a hybrid car is a mixture of a gas car and an electric car. This is a mixture of an s orbital and 3 p orbitals to give you 1, 2, 3, 4 sp3 orbitals, and you'll notice that they're the same level of energy, so they will form identical bonds or equal in energy bonds. 1, 2, 3, 4 equal energy bonds. So that's an sp3 orbital. And at this point, I want to point out that there are 1, 2, 3, 4 of these sp3 orbitals, and if you look at the sp3 notation, you'll notice there's 1 s and 3 p's, and that adds up to 1, 2, 3, 4. So it makes sense that we call them sp3 hybrid orbitals. So here's a little picture of what is happening. So we have our s orbital right here, and our 3p orbitals right here, mixing to form 1, 2, 3, 4 sp3 orbitals, and the geometry or shape you would get would be a tetrahedral shape, just like you would get, up here, tetrahedral, because you have 1, 2, 3, 4, 1, 2, 3, 4 electron domains around your central atom, which would be right in here. So just to review, an sp3 orbital is that when you have 1 s orbital and 3 p orbitals, and they combine together to make 4 sp3 orbitals. Okay, let's talk about sp2 hybrid orbitals. So sp2 hybrid orbitals, again, we're gonna focus on carbon. In this case, we're gonna focus on this carbon right here, and what's happening to that carbon. So that carbon started out, of course, with an orbital notation with a promoted electron. So I'm just going to go ahead and take the electron that was here and put it here, like this. And it is going to hybridize by taking 1s and 2p orbitals, and it's going to mix those. So what you end up with are 3 sp2 orbitals made of 1s and 2p orbitals. So you've got 1s orbital that was this orbital and these 2p orbitals here, and they mixed. They're at equal energy. And then you've got this leftover 2p orbital that's unhybridized. So it's an unhybridized atomic orbital, or a p orbital, that didn't mix. So what that might look like in a picture form is you've got your s orbital and your 1, 2 p orbitals that it's going to mix with, and then the 1 orbital that remains unmixed. So you'll get your 3 sp orbitals, 1, 2, 3 of your sp orbitals, and then your 1 unchanged p orbital. And the type of geometry that you're going to get surrounding something like that. So for example, this carbon right here, you know, you've got 1, 2, 3 electron domains. So 1, 2, and then 3 electron domains. And we'll talk about this will be your double bond, and this will be the single bond right here. You'll get a trigonal planar geometry associated with sp2 hybrid orbitals. So let's review. For an sp2 hybrid orbital or hybridization, one of your s orbitals is going to combine with 2 p orbitals to make 3 sp2 orbitals and one leftover unchanged p orbital. So the last type of hybridization we're going to talk about is sp hybridization or sp orbitals. So in this case, you are going to have, and if you look at it, it makes sense, sp, so 1s and 1p. So the 1, 2s and the 1, 2p orbital are going to mix. So you're going to get 2 orbitals that are called sp orbitals, and then you'll have your leftover 2p orbitals up here that remained or that are unchanged. Of course, nothing happened to our 1s orbital because nothing happens to the 1s orbital because it's not valence, right? And you end up with your hybrid orbitals right here. So there's your sp hybrid orbitals. And of course, your unchanged atomic p orbitals that didn't hybridize, right? So they're unchanged. So here's a picture of what that would look like. Your s orbital here, sorry, yes, and one of your p orbitals here, mixed to make 2 sp orbitals, and then you've got your leftover 2 p orbitals right here that remain unchanged. The geometry you're going to get, of course, because you have 2 electron domains around your carbon, so we're focusing on that carbon right there, is a linear geometry. So, and let's review very briefly. For an sp hybridization, 1s and 1p combine to form 2 sp orbitals, and then you're left with 2 unchanged p orbitals. So how do you tell what sort of hybridization you have around your central atom? Because the fact of the matter is that hybridization happens to a lot of elements, not just carbon. I used carbon as an example because it does all 3, but most central atoms in molecules will hybridize. And so how are you going to know how they hybridize? So you're going to look at the Lewis dot structure and count the electron domains around the central atom. If you find that you have 4 electron domains around the central atom, that's going to be an sp3 hybridized central atom. If there are 3 electron domains around the central atom, you will find that that's an sp2 hybridized central atom. And of course, if there are 2 electrons around your central atom, that's an sp hybridized central atom. So just know that 4, I mean, look at it, it makes sense. S and 3 p's adds up to 4. 3, 1s and 2 p's adds up to 3. And then 2, S and P, at 1s and 1p adds up to 2. So it's easy to remember the trend. Let's do an example. So here's the Lewis dot diagram for water. And we want to know the hybridization of the oxygen, the central atom. So we're just going to count the electron domains. There are 1, 2, 3, 4. So 4 electron domains around that carbon means, or around that oxygen means that the oxygen is sp3 hybridized, or that its orbitals are sp3 orbitals. Or how about this molecule? Let's look at the carbon in the center. It is surrounded by 1, 2, 3 electron domains, which means that if it's got 3 electron domains, then it must be that carbon is sp2 hybridized, or its orbitals are sp2 orbitals. Okay, let's look at one last one. This silicon, I want to know its hybridization, so I'm going to count the electron domains. 1, 2. Remember, double bonds still count as one electron domain. So that means with 2 electron domains around the central atom, that silicon is sp hybridized. So that's it. That's hybridization in a nutshell.